Hello everyone. Today we are going to look at the second part of section 4.1, which is all about Newton's laws. We're specifically going to look at Newton's first and second laws today. So our targets today are to examine the relationship between force, mass, and acceleration. Mass is a new concept for us. And we are going to see if we can identify instances of inertia, and that will be Newton's first law. The questions we're going to try and answer today: what is the relationship between force and acceleration? Why do some objects resist motion? Okay, but we're going to start with review. I always like to, start with where we've been and how it all fits together. So if you recall from last time, a force can be one of three things. It can be a push, a pull, or a twist. Forces can be contact forces that happen because you're touching something, or long-range forces like gravity, where you don't actually have to be touching anything. We also know that with force, just like velocity and acceleration, the size of the force matters and the direction of the force matters. These are both important things. That makes it a vector quantity, just like position, velocity, acceleration. Okay, so we're going to pay attention to direction. That's going to be really important. And we know that forces can cause acceleration. As a matter of fact, they do cause acceleration. So if you think back, you will remember that acceleration is a change in velocity over a change in time. All right, so get all those things kind of together in your mind, and that's where we're going to start today and move on and talk about Newton's first and second laws. So Newton's first law has two parts. The first part is that force can cause motion to change. We just said that because that's what acceleration means. All right. So an object's motion is not going to change or won't change unless a force is applied. So here's the example we're going to look at here. Example A, this bowling ball is just sitting on this bowling lane. It's not going to spontaneously roll down the lane all by itself, right? You're going to have to do something to it. You can push it with your hands or your feet. I don't really know how you pull it. I guess you could get in front of it and pull it. And I guess you could twist it too. But anyway, it's just going to sit there unless you do something to it. So this bowling ball has what we call inertia. It's not going to change unless some kind of force acts on it. So we're going to say that the bowling ball sitting on the floor will continue to sit on the floor until a force causes it to move. Okay, so that is an example of inertia. This object is not inclined to do anything unless some force acts on it. You could even have an earthquake, right? That would be a force that would cause the bowling ball to move. All right, so that's the first type of inertia. Second type of inertia, and here is our second example. Now this bowling ball is supposed to be moving. So this bowling ball is going to roll. It's going to continue to roll until it runs into something, right? A pin or a wall or your foot or something, okay? And so the fact that it's rolling and will continue to roll is a kind of inertia as well. So this bowling ball rolling across the floor will continue to roll across the floor until a force causes it to stop. This is also inertia. The tendency of a moving object to keep moving, right, until something happens to it. All right, so we're going to stop here for just a second. This whole idea of objects moving or not moving until a force acts on them, that's Newton's first law. And so I want you to pause the video for just a minute. I want you to kind of summarize that in your own words. And off to the side, if you have any questions, go ahead and write them down and we can talk about them in class next time. All right, so let's keep going. Here we have one new term that we're going to need in order to talk about Newton's second law. So mass is the amount of stuff. I know that's really scientific, huh? In an object. You can think of it as matter, you can think of it as molecules, but Mass is the amount of stuff in an object. Generally, bigger things have more mass and smaller things have less mass. It's not totally true all the time, but in general. Mass gets represented by the letter M and is measured in units called kilograms. Now, next year when you take chemistry, or maybe you've already taken chemistry, you are going to measure things in grams, but those are for small things. We measure big things like bowling balls and cars and rockets. So we are going to measure things in kilograms, okay? So Newton's second law essentially tells you the greater the force that acts on an object, the greater the acceleration. In other words, if you push something harder, it's going to accelerate more, right? That makes sense. Newton's second law also says the greater the mass, the smaller the acceleration, which also makes sense. Okay, so the bigger something is, the more you have to push it in order to get it to move or stop moving, right? So the greater the force, the greater the acceleration. The greater the mass, the smaller the acceleration. Okay, so those are how those three things are related to each other. And if we were to write that as a formula, we would say acceleration is equal to the net force divided by the mass. Or you will often see it written as the net force is equal to mass. I don't know why I wrote that up there. Hang on, let's try that one more time. Mass times acceleration. All right? F stands for force. We measure that in newtons. M is mass. We measure that in kilograms, we just learned. And A, of course, is acceleration. And we measure that in meters per second squared. Good for you. Okay? So this is how Newton's second law kind of all fits together. So I want you to take another moment, pause the video, and repeat that to yourself or say it in your own words so that you are confident about how those things relate. All right, thank you very much. Let's go ahead and look at our first two our next example. So we have student who is pulling 3 friends on a sled with 27 newtons of force. That's going to be important. The mass of the sled is 67 kilograms, and I would like to know what is the acceleration of the sled, and I get to ignore friction in this problem. All right, so we'll write down what we know. Oh, I should probably make this a little bit smaller. Okay, so I know that the mass of the sled is 67 kilograms. I know that's the mass because it's in kilograms. I know that the force on the sled, so the pulling force on the sled is 27 newtons, and I would like to know what the acceleration is. All right, so let's draw our free body diagram and get ourselves organized here. So here's the middle-ish of my sled. I have a force. We're going to pretend that this sled is on the ice. So I have a force of the ice on the sled. I have, what's this one going down? Good for you, the force of gravity. Now those two arrows should be about the same size because this sled is not moving up or down. Okay, so those two forces need to cancel each other out. I have a pulling force going in this direction. And I know that this is 27 newtons because it told me so in the problem. And I have a friction force going the other way, but I get to ignore it. So we're going to kind of do this. We know that force is actually going that way, but I get to ignore that one. Okay, so in this case, I can say that the pulling force is going to be equal to the net force, right? Because the ice force and gravity cancel each other out, so that goes away. And then what's left is the 27 newtons. Oh, I almost forgot to say, we're going to call this positive. Okay, so I can say that my pulling force is equal to my net force. So when I write my equation, I'm going to have A equals F net force over M. And so I'm going to have 27 over 67. And that is going to give me an acceleration of 0.40 meters per second squared. Now, you're going to look at that and think, wow, that's really slow. What a boring sled ride. Remember, that's not the velocity, right? That's the acceleration. So that's how much the velocity is changing. So it'll be slow in the beginning, but if the student keeps pulling, it's going to get faster as we go along. All right? So again, if you have questions, go ahead and write them right there so that when we go over these notes next class, we will be able to answer your questions. Let's look at the second example. All right, so now I have a student pushing a 150 kilogram hot dog cart. The cart has 0.45 meters per second squared of acceleration, and I'd like to know how much force is the student using, and I get to ignore friction again. So if we write down what we know that the mass, that's not helpful, the mass is 150 kilograms. We know the acceleration is 0.45 meters per second squared. And I would like to know what's the net force, right? How much force is the student using? So we need to draw our free body diagram here. So again, there's my dot in the middle. I have the force of the street. That's hard to read. Going up, I have the force of gravity. Going down, again, those are going to be about the same size because they cancel each other out. I have a pushing force going in this direction. And I know that that is what I'm looking for. I also am going to decide that this direction is positive because I like to work with those positive numbers. Okay? So let's come back over here and decide some stuff. So again, because gravity and the street cancel each other out, my net force is going to be equal to my pushing force. So if I can solve for the pushing force, I'm good. So net force is equal to mass times acceleration. If I put in 150 kilograms and 0.45 meters per second squared, that is going to give me a net force of 68 newtons that student is pushing the hot dog cart with. Okay. So again, if you have questions, make sure that you write them off to the side there. Here are the two problems it's your turn to do. You are going to do the same thing that I did. You are going to write down the important information. You're going to do the free body diagram. Go ahead and solve for what's missing. And again, you are going to ignore friction in both of these problems. All right? And I will see you in class next time. Thank you very much.